All right, hello everybody. Friendly welcome from our good friend Forrest Gump here. Um, Today we're going to talk about waves. For a couple days, y'all have been asking me how we know that there are different layers to the Earth, and I've been telling you, well, we're going to get to that. We're going to get to that. Well, here we are. Waves are how we know that the Earth is not just made up of one material all the way through, but that we have different layers. And I'm not talking about this kind of wave. I'm talking about waves of energy. Now, in class, we watched this video. It's just the people getting owned by the ocean. You can watch that if you want, but we're going to move forward right now. So, first of all, what is a wave? Really, a wave is how energy gets from one place to another. So, when energy is traveling, it's going to do so in a wave. We've got two different kinds of waves that we're going to talk about today that, that specifically involve the Earth. So, we've got P waves and S waves. S waves are the one that looks kind of like this. If you were going to hold a rope and wave it up and down when it's tied to a strong surface over here, you're going to see this nice like mountain and valley formation. And that's how that's how the energy is moving through that rope. So that is an S wave. Another type of wave we're going to see is called a P wave. So if you had a spring and you were to like stretch it and relax it, stretch it and relax it, you're going to see these vibrations that are moving back and forth through the spring. These different areas where it's spread out versus different areas where it's more condensed. So this time it's not going to be an up and down motion. It's going to be a compression and a relaxation motion, but it's still energy traveling through a substance, right? So the Earth has S waves and P waves that travel through it as well. We're already pretty familiar about waves traveling at different speeds, even if we didn't realize that we were. So I'm sure many of you have noticed at one point or another that if you put a pencil in a glass of water and you can see through the edge, it looks like the pencil is broken, right? And then if you're a little kid, you're noticing this for the first time, you're like, oh, my pencil broke. And you pull it out and you're like, wait a second, the pencil's fine. And you put it back in and it's just really confusing. The reason this is happening is because the light is reaching your eyes through different substances. So through the air versus through the water. And when light travels at or when light travels through different materials, it travels at different speeds. And when it travels at different speeds, it bends. So, like for example, right here, it hits this, it bends, it comes back out into the open air, and it is still changing direction. So, when a wave travels through different substances, it can change direction as well. So, we know that the Earth has different layers because of waves. So we have waves happening all the time through the Earth because of earthquakes. Earthquakes happen, it sends shock waves through the Earth. And if this were all one substance, we would see them just traveling straight through the Earth with no bending. But what we see is a bend in direction. So we have these locations all over the world where we're monitoring the different waves that reach Earth. And so whenever there's an earthquake, all these different centers are kind of interconnected and they communicate with each other. And they say like, oh, this is when I received the wave. Oh, this is when I felt the earthquake. And because of that, we know how these waves are traveling through the earth, not across it, not around the surface, but actually through the earth. So they're bending as they hit these layers and ending up in different locations based on what they're made of. So this is kind of like the pencil being put in the water. It's bending differently than it would have if you were just looking at the air or looking at the pencil being held, just in the open air. So this is how P waves move through the earth. They can travel through all these different layers, but when they hit this outer core right here, which is made of liquid, they bend. So it's traveling through a solid here, and then it bends when it hits the liquid, it bends when it leaves the liquid, and then continues on its path. Well, S waves work a little bit differently. So S waves, as you can see right here, as they can travel through these solids as well. Here's their normal path. But as soon as they hit this liquid outer core, they stop dead in their tracks. because an S wave cannot move through a liquid. So, as these different centers that are located all around the world are relaying messages like about the different P and S waves that they're receiving, if you're on the opposite side of the world compared to where the earthquake began, you don't receive any S waves. So, I'll say that again. If you're on the opposite side of the world compared to where the earthquake happened, you don't receive any S waves. And we know from doing tests just on the surface of the earth that S waves can't travel through water. So that leads us to believe that this outer core must be at this location and it must be made of liquid. Otherwise, an S wave could have gone through it. Okay, that's all I've got for waves, and that's how we know what the Earth's layers look like. We can't measure them directly, right? We can't go down there and check to see what they're made of. We can use indirect evidence to get a good idea of where those layers are and what they're made of.